octopods, elephant trunk, snakes. What is the first thing that came into your mind when you hear these words? Yes, they all belong to the animal kingdom, but how are they related to robotic? Well, good afternoon, everyone. Welcome to the robotics session of ESEC 2019. My name is Vicky Chen, a second-year Eng Sci student. And today, I have the pleasure to introduce our guest speaker, Dr. Jessica Burgner-Kahrs. Elected as one of the top 40 under 40 in the category Science and Society 3 years in a row, Dr. Burgner-Kahrs is leading the way in the area of continuum robots. Inspired by nature, these robots are fitted with tentacle-like arms mimicking snakes, elephant trunks, or octopods to access difficult-to-reach space with minimum invasions, therefore creating new possibility in surgery. Her outstanding achievement in the area of robotics is recognized by multiple organizations across Europe. She was awarded with Hans Meyer Leibniz Prize, the Lower Saxony Science Award in the category Young Researcher, and Young Researcher of the Year 2015 in Germany. Since 2015, she has headed the Laboratory for Continuum Robotics at Leibniz University Hanover, and this year she is going to join University of Toronto as an associate professor, and she is going to bring her robotic lab to Toronto. So for those of you who are interested in robotics, be sure to pay attention. You will not want to miss a word. Ladies and gentlemen, please join me in welcoming Dr. Jessica Burgner-Kahrs.
Well, good afternoon, everyone. I want to start off with thanking the organizers. Like, you have organized a tremendous conference. I'm really impressed by the organization. I'm really impressed how you treat us as speakers. So thank you very much. You did a really, really good job. I'm really enjoying my day here so far. It's a great pleasure to speak in front of you. As you have heard, I will join the University of Toronto starting April 1st, so I'm really excited to be here in January and also use the opportunity to meet you all. I've been talking to some of you already, and I'm really happy to talk to so many bright students that are so ambitious about what they're doing. That's really a big pleasure for me. So today, we are going to talk about my favorite topic in research. It's continuum robotics and how those are going to change our future. I want to start off with asking you a question, or maybe think about this question for a little bit. The question is, how does a robot look like? Think about this question for a little bit and just imagine a picture of a robot in your head. Some of you might have thought about some of those robots, right, that you know from movies. I really like Disney movies. I really like Pixar. Like, I really loved the WALL-E movie. Really liked it with Eve, and it was just so cute and so heartwarming for me as a roboticist. Or maybe you know Baymax from Big Hero 6. Really cool movies. And these are robots that are fiction, right? Maybe you also think about Star Wars, R2-D2, and all those kind of stuff. So actually, robots in the real world don't look like these robots at all. Some look like humans, mostly research systems. You can see here, so they are humanoid robotics. They take inspiration from how we as humans look like. You can see there's a torso, there are arms and legs, and it's pretty much resembling our stature. Now, these are still in research. So what you see in everyday automation industry is those kind of robot arms. It's serial robot arms. So they are inspired by the human arm. So you have several joints connected by rigid links. And so you can move this robot arm around very precisely, do repetitive tasks. For example, in automobile industry, lift heavy parts, do laser welding, and so on. So really good to save some human labor and do all those kind of tasks that are really tiring for a human. So these are very typical. There are thousands, millions of those working as we are speaking. Then there's also those kind of robots that are used in industry very much. It's called a parallel robot. You can pretty much see the difference. So the joints are not in series. They are arranged in a parallel fashion. Those have smaller workspaces than those robot arms, but they are very, very precise. So for example, they are packing chocolates in little boxes all the time, or all these kind of sorting tasks where you really have to do repetitive things very quickly. Then there are service robots. Some of you might have seen some of those. I really love the one up here. That's my favorite robot at home. It's my vacuum cleaning robot. big help for me. Goes vacuum cleaning. I can sit on my couch, have my coffee. Anyway, also at Amazon, all the warehouses, all logistics tasks, you have a lot of those mobile robots that are carrying around logistic items on a daily basis to make delivery faster for us. So these mobile robots have wheels, obviously, they wheel around. There are some that also use these robot arms on top of them, so you drive somewhere and then you can grab things, move them around. There are also underwater robots, swimming robots for marine tasks. And then there's also this big area of surgical robotics. This is the Da Vinci surgical robot, a very successful surgical robot system where the surgeon is actually seated here at a console and he's looking inside the human body because the robot arms carry video endoscopes. They are put inside the abdomen, and so the surgeon can perform surgeries within the abdomen, for example, removing the appendix or gallbladder resection. Anyway, so when you look at these robots, they all have rigid links and joints. And that's why when I think about robots, I think about my favorite animal first. I'm thinking about elephants. Ever since I'm a kid, I'm very impressed by elephants. They are just amazing. And when you look at the elephant trunk and what it's able to do, it is actually super impressive. Like, it's not only their nose, like, it's also good for them to reach places that are very hard to reach. So the elephant trunk is a very dexterous item. It can smell, obviously. You can see it can bend in many degrees of freedom. It can be used to grab food. It can also be used as a weapon in some cases when male elephants kind of fight for the female elephants. Anyway, they use it to grab objects and put them in their mouths. They also drink. So use water, and they can also extend and contract even when you look closely. And where does this high dexterity come from? Where does this motion capability come from? So fun fact, when you look at the robot skeleton, what becomes very apparent where the elephant trunk is, there's no bones, no rigid links, no joints. So what's the elephant trunk made of? The elephant trunk is a muscular hydrostat. You can see this here in this beautiful plastination from Gunther von Hagens. He does body works and also animal works. So this is an elephant that he plastinated, and you can see that the trunk here is a huge muscle. It's composed of 40,000 individual muscle fibers that can be actually contracted in different patterns, such that the elephant trunk can do all these motions that you have been seeing. So no rigid links and joints seem to be a good idea in order to be dexterous and in order to perform all these different motions with an elephant trunk. I'm also sometimes thinking about anteaters. Anteaters are pretty cool as well. So they have the longest tongue in the animal kingdom. It's the mammal with the longest tongue. It's up to 60 centimeters in length. It's ridiculous given that it's very small in diameter, only 10 to 15 millimeters. And so the snout of the anteater is very long, and it's actually very useful for the anteater to get to its favorite food, its ants and termites. So it can really reach these hard-to-reach places with its tongue. You can see this very nicely in this video installation. So it's a plastic bottle with honey. And you can see the anteater with their tongues trying to reach the honey. So it's a pretty amazing organ when you ask me. So the question that I'm asking myself then, why are we not building robots with no joints? It seems to make a lot of sense when we look to the animals, right? We have seen these tongues, we have seen trunks, we can also think about worms, snakes, all those sort of animals that are able to sneak around, that are able to turn corners, reach objects, and really get into the heart of things. So robots with no joints is really what I'm interested in, and that's continuum robotics. So what is the definition of a continuum robot? What does that word even mean? Ian Walker, a fellow continuum robotics researchers of me from Clemson University, he made this definition, which is very closely related to the animal kingdom. He says continuum robots can be viewed as being invertebrate robots as compared with the vertebrate design of conventional rigid link robots. Continuum robots can bend and often extend and contract and sometimes even twist at any point along their structure. That's a very good definition. We, some colleagues and I, we made a more mathematical definition. That's easier to grasp for us engineers, right? So we say a continuum robot is an actuatable structure that differentiates it from being not a robot, whose constitutive materials forms curve with continuous tangent vectors. Now, you can deal with this, right? You had algebra already. Anyway. So that's what a continuum robot is. How does it compare with the conventional robots that we have seen? Let's categorize that. So the conventional robot arm, you can see on the left-hand side, is a so-called hard robot. It's composed of hard materials, usually. It's usually non-redundant, meaning it has only the number of degrees of freedom that are necessary to be able to put itself in Cartesian space. Meaning, if you want to position and orient yourself, you need 6 degrees of freedom. So, talking about redundancy, so if you add an additional joint, for example, our shoulder joint, you add redundancy. So I can grasp this position and maintain the orientation of my hand while I'm moving around my arm, right? So this is redundancy that I have. So you can think adding more redundancy means you have more degrees of freedom to actuate and more degrees of freedom to arrange your robot. So when you drive this to a more extreme case, you add more redundancy. You can compare that with like the spine structure or like having very many joints put after each other, right? Now you can think about the link lengths becoming shorter, the number of the joints getting closer to each other. So approaching infinity, you would reach a continuum, right? A continuous structure with no joints. And that's where continuum robot lies in the spectrum. And you can also probably heard about soft robotics. That's also a very hot topic in robotics these days. Soft robotics is like a subcategory of continuum robots. It's all those continuum robots that are made of very soft material. All right, now that we all know what continuum robots are, let's talk about history of continuum robots. The first continuum robot, most surprisingly to me, was actually developed in 1965. That's around the same time that the first serial robot arm was used in an automobile factory. So this robot was developed by 2 students, Scheinman and Leifer, at Stanford University. It's the ORM. The ORM is a cool robot. It's pretty short. It can only bend in 1 degree of freedom, but you got to consider it's 1965. So what you can see here, it has these bellows in between metal discs. So it's pneumatically actuated. And so by changing the pressure in those bellows selectively, you can actually make this robot bend. Nobody ever continued this route of research back then. So it's now on display in the Computer History Museum in Mountain View, California, so we can actually see this thing. And when you look closely, it's not even a continuum robot, to be honest, following our definition, because when you look really close, you can see that there are links in between those disks. But anyway, it's kind of the first type continuum robot. Then still 1965, there was another first. It's the tensor arm. It's a little bit of a different structure, so it doesn't use pneumatics, but it's using tendon actuation. So you also have those disks, and then you see there are tendons routed through these disks. They are terminated at different disks, so you can induce bending moments and can achieve this snake-like behavior. Then there's this little gap in history right here. Long time, nothing happened because people were able to build these simple continuum robots, but they were not really able to model them. They were not really able to control them. So nothing really advanced until 1980, when Professor Hirose at Tokyo University started a whole era of snake-like robots. And some of his snake-like robots were also continuum robots, like the one you see there. It's using a spring as the main structure. And you can see it's also those disks. That's kind of a continuing way to do it. And then it's also using wire actuation in order to have this bending motion. Now we're going quickly over some other examples from history. This is 1989. That's when people used shape memory alloys, so shape memory springs, in order to induce bending motions. They have built an active endoscope. It was intended for medical application, never really used in medical application back then. because with shape memory alloys, it's always a problem to, the dynamics are always not as great because you have to heat the spring and then it has to kind of cool in order to get back to its original state. 1991 was then exciting. This is when the first soft continuum robot was built. It was also at Tokyo University. It's pneumatically actuated. It's pretty small, so it's, look at the diameter. It's going to decrease in the course of this video even. So it's a silicone structure. It has 3 chambers, and then the chambers are pressured differently, such that the robot can bend in 2 degrees of freedom, which is very cool. So here you can see these 3 chambers in the middle. And you can say by increasing the pressure in just one chamber, right, you can make this amazing motion. Now this is even only, this is 2 sections now. It can bend, so both can bend, right? You see the supply lines at the end. It's a pretty cool thing. And it can also twist if you have, like, there's some fiber reinforcement in the structure, so you can also induce a twisting motion if you like. So you can assemble fingers, right? That's a little gripper. It's pretty useful. Pretty impressive, right? No rigid link, no joints. It's just the simple silicone body, and it's just actuated by some pressure differences. So it's pretty cool work that they have been doing back in 1991. We're going to jump a little bit in history to 2010. That is when the first continuum robot was commercialized. This is Festo, a German company, and they built this bionic handling assistant. It is inspired by the elephant trunk, as you might tell. It has 3 sections, and when you look closely, you will remember the very first continuum robot because it also used this bellow-like structure on the inside. So it's also pneumatically actuated, and then you have those bellows here in order to give the structure to the system. It's a pretty cool robot. They have been developing it over the last couple of years. This is the recent version from 2017. And then there has been another one by ESEC Robotics. It's a UK company that has been purchased by GE Aviation just last year. And they built the longest continuum robot that is out there today. So it's 5 meters long, 3 of which can be actuated. And you can see her teleoperating this robot by reaching how to reach place because it's high up. But you might also tell, well, but the curvature is not really that impressive, right? I mean, you could also use a ladder to go up there, but still. So these are 2 commercially available continuum robots. But the problem is, so they are not really used that much. And that's because they have a size which is comparable to the serial robot arms we have been seeing earlier. And they cannot really do more than a serial robot arm. In fact, they do worse, because the accuracy that those robots can achieve is usually an order of magnitude lower than what a serial robot arm can, right? It's less stiff, the compliance is really high, and so that's an issue. So there's no real benefit with these big continuum robots, to be honest. I mean, they're cool to look at, very nice, but not really that useful. And that's why I am looking at more challenging tasks, those tasks that are not possible to realize with conventional robots these days. For example, all sorts of tasks which are characterized by limited access, by tortuous paths, and by tasks which also require manipulation once you get where you're going. For example, inspection tasks. One example is maintenance, repair, and operation in aerospace. So that's a common jet engine. I flew here from Germany 2 days ago. So those jet engines are actually maintained on a regular basis. You have to check the inside of the jet engine quite often. That such incidences, as happened last year, for example, with Southwest in think it was beginning April, don't happen. What happened with this is, so the Southwest flight took off from New York, I think, and the engine blew off in the middle of the flight. And so there was actually part of the engine opening, or like part of the engine just destroyed one of the windows, and the passenger was thrown out and she died. Like, that was devastating. And it was due to material fatigue within the engine. So one of these turbine blades within the engine got fatigue, and so it broke, and so the whole engine blew off. And you usually have a technician, as the guy you see in the background, that is inspecting the different parts of the engine for any fatigue. And this is a very, well, cumbersome job, because he's using a flexible endoscope to be moved inside the jet engine, and he's inspecting it visually, and it takes a lot of time. So this is a task where a robot could be really useful. Think about a small continuum robot that would sneak inside this jet engine automatically and just inspect all those blades for any material fatigue, any cracks that you might see. Or think about minimally invasive surgery. Think about applications in surgery. Think about you have a tumor in the center of your head, like at the pituitary gland, as you can see there. It's right at the center, and it's really hard to reach. Usually surgeons have to open up your skull to operate down there. Think about a continuum robot that could sneak up your nose, go to the middle of your brain, remove this tumor, sneak out, and you're done. You can go home. Or think about nodules in your lung that could be removed by a continuum robot that's sneaking through your bronchi. Or think about other natural accesses to our human body, right? Just the route down there. You can go pretty many places. Think about the kidneys, think about the bladder, think about all sorts of diseases that you could actually prevent by having a continuum robot using this route, rather than having a big scar on you. So with these applications in mind, one of the big research questions that I'm asking myself is, how can we build small-scale continuum robots that are able to accommodate and accomplish those tasks? It's not too easy, to be honest. You are engineers, you can probably relate to this. So the design space to build a continuously bending compliant structure is diverse. It's just enormous possibilities that you could use. Also looking at the state of the art, there has been a lot out there. At the same time, you will only be able to control a limited amount of degrees of freedom, right? You cannot control all the degrees of freedom that you theoretically have. And at the same time, and that's probably even as challenging, is that designing robot with soft and elastic materials is somewhat unfamiliar. Like, most of the robots have been built from hard material. So what the research community in continuum robotics kind of for now did, we differentiate between extrinsic and intrinsic actuation. You've seen some of the intrinsic one in the state of the art that I showed you in the history. So pneumatic, hydraulic, or even shape memory alloys. That is actuation within the robot structure itself. Usually it's hard to miniaturize the robot even more than, right? Because you have to have some space to integrate your, for example, pneumatic valves, your pneumatic lines, and so on. So that's why extrinsic actuation, having the actuation outside of the robot itself, is usually probably more helpful if you want to miniaturize your robot. And that's the part of my research is mainly focusing on extrinsic actuation, the thing you see on the top, like tendon cable actuation or concentric tube robots. And this is the part that I'm going to talk about today a little bit more. The simplest way is to build a tendon-actuated continuum robot. You have some elastic backbone in the center, and then you use these tendon routing discs to route your tendons. You terminate them at different points along the structure. Then by pulling on those tendons, you can induce bending moments, and you can make your robot bend around. That's what researchers have done for many years. The problem is that the segments, so where the tendons terminate, are fixed in their length. That means that the radii of curvature is limited, and that makes it very hard for the robot to deploy into a tortuous path. So that's why we have come up with extensible segments, a way to make those extend and contract. And when you look closely, you might think, but that looks like this tendon-driven robot from the slide before. True, but when you look closely, you see there's the sandwich here between those tendon routing discs. Looks like two discs. And it's right, because in the middle of those two disks, there are permanent magnets. And we use them at alternating polarity orientation, such that we extend and contract the robot, that they distribute evenly by contracting or by repelling themselves. And how we extend and contract is that the backbone, when you look very closely, is not actually just one structure. Here you see the diameter is smaller than down here, so it's concentric tubes. It's super elastic tubes that we put inside of each other, and then by extending and contracting these tubes, we can use this extensibility. This is how such a robot would look like. It is 7 millimeters in diameter, 3 segments that can be individually actuated, and they have a length between 15 and 70 millimeters. So you can see the range of motion is pretty cool. It's pretty impressive. So you can see this robot being very useful in some of those applications we've been talking about earlier. So it's really cool, and you can see as soon as it gets into contact with the environment, it's compliant, so it's not really a big safety concern when it's close to humans and when it's in some environments that are fragile or within the human body. Now, the tendons have been routed in parallel so far. We have also been investigating what happens when you route these tendons in different paths. Here it's a helical routing, so the tendon is routed helically around it. And now you see when you pull on the tendon, you can actually observe it's not only a bending motion, but there's also a twisting motion. So you have both at the same time, which is really interesting. We have looked at different types, and you can see it can be very beneficial for obstacle avoidance or for grabbing objects, for example, because this additional twist really leverages the design. And this is another tendon actuated continuum robot. Sorry, that's a German patent that we just got. So it's just a shaft mechanism, that's what the word says. So it's a spring on the outside, so there's no backbone on the inside, and then it's also tendon actuation, and for the stability we also use these springs. And you can see by pulling on the tendon that this is behaving like really nicely. It conforms to the environment. It can be used as a gripping device, for example, and it conforms very nicely. Now, these type of robots are very well suited for this maintenance and operations for inspection tasks. There are 7 millimeters, maybe we can go down to 6, probably even 5, but from then on the bending moment is just not enough, right? Because the tendon comes closer to the backbone and you wouldn't be able to induce more bending. They're pretty cool. But now let's think about this sneaking up the nose to your brain and, you know, the other route. Still pretty big, so we would want to go smaller. So can we build even smaller continuum robots? With this principle, no, because physically we are just approaching the boundary. So we have to come up with a different solution, with a different idea. And the solution that we came up with was inspired by a telescopic antenna. Probably, well, honestly, probably most of you don't even know what that is. When I was young, we had this radio at home, right, where you would need to pull out this antenna. I remember this being cool. Anyway, telescoping antenna. So you have tubes with different diameter, right, that you can pull out of each other. And that's the main idea behind the smallest continuum robot. So this concentric arrangement of tubes. It's just that the tubes that we're using are not stiff tubes. They are super elastic tubes. They are made of a shape memory alloy. It's nickel titanium. And the good thing is about nickel titanium, when it's in its super elastic state, it can recover high strains, as you can see at this video, right? So the tube is pulled out of its original shape, and then once you release the strain, it returns to its initial configuration, which is a really cool feature, which we can use in this robot, the smallest continuum robot worldwide so far. It's this 0.5 to 2.5 millimeter in diameter robot. It's 3 concentric tubes. When you look closely, so you see that's the tip, that's a little gripper. That's the first tube, and here starts the second tube, and then, oh, I think the third one is out of the picture, but anyway. That's the idea behind it. You put those tubes concentrically inside of each other. They are not straight, but they are pre-curved. And then by pushing and pulling those tubes, you can achieve a tentacle-like motion at a very, very small scale. You can see that here in the video. So that's the actuation. It's all mechanical. So it's pushing and pulling and also rotating. And that's these 3 tubes. Look closely, you can see all 3, right? So now they are all pushed out of each other. And then you rotate them also. And then you can see it's this, yeah, it's comparable to a tentacle in terms of motion, but it's only 1 millimeter in diameter. And the cool thing is, so the most inner tube offers a channel to the tip. So you can really insert whatever you like a little gripper with like a wire that you can actuate to open and close the gripper. You could include a laser fiber. You could include other sensors. You could also use it to deliver drugs or get biopsies from within the human body. And with this small robot, you can really reach any place. So that's a really cool continuum robot that we are very proud of to be working on. Now, in this you obviously can think about many surgical applications. Just to give some examples, for example, in abdominal surgery, or for example, fetal surgery, where you really want to go through a very small incision to operate on the fetus. Okay, I want to do a little commercial break because, you know, it's the last talk of the day. You're probably all tired and think about, wow, what's she talking about robots? I want to go to the reception. Almost. So commercial break is just to advertise a little bit. As you heard, I'm coming to the University of Toronto starting April. I'm going to work on the Mississauga campus in computer science because we are going to kick off a robotics program in computer science as well. And this is one of my future colleagues. It's Florian Schutte. He should be in the audience. Are you here? Maybe, maybe not. No. Well, anyway, you see him on this picture. You will see him around. So he is going to be an assistant professor. He started in December. And his research interests are in mobile robotics, machine learning, computer vision, and imitation learning. Just for you to know, so if you are interested in some of those areas, you might want to contact him. That's his website. That's his email. So Florian is a really good guy. So in case you're interested, he's also doing swimming robots. So that could be really, really cool. And this is my other new colleague, Animesh Garg. He's going to start in the summer, also at UTM. He's currently at Stanford. He is interested in personal and surgical robotics, so more like robots for your home, to be helping in the kitchen, for example. Also surgical robotics. He's more a reinforcement learning guy, in case you're interested in that. And he's also interested in computer vision. So he's coming in the summer, also his website and his email, in case you're interested to contact him. All right, coming back to continuum robotics. Elephants are really cool, right? As I said, my favorite animal. But as you see here with this baby elephant, it's really hard to control this trunk. So it really has to learn how to deal with it. What's happening here is this little elephant probably doesn't have a good model of its trunk yet, right? It needs to coordinate all these muscles and kind of understand what's going on. You see it's like wobbling around, and he cannot really control it well. Motion planning could also be improved, right? He's not really doing a good job on that. And control obviously is a little bit concerning. All right, so that's the 3 topics I'm going to talk about in the last half of my talk. So how can we mathematically describe a continuum robot? That's not as easy. When you look at conventional robots, it's usually very easy geometric relationships that you can use. You know, you can have these arms, the links, the angles in between, and you can pretty much easily compute where your tip is. For a continuum robot, it is not that easy, to be honest. So what we are interested in is we want to input a configuration. Meaning, for example, where do I put these tubes? How much do I translate them and rotate them? Or how much do I pull on the tendons? That's going in. And if I'm able to measure it, I want to also know what external forces and moments are acting on my robot. And then I want to have a model that gives me the red dotted line, which is essentially the shape of this robot, a curve in 3D space, ideally giving me the orientation of the material at any point along the length. If I know all that, I'm good for motion planning and control, but I need to be able to obtain this relationship. And all the techniques that you use in conventional robotics do not apply here. So we got to go a different route. And the route we are going is using elasticity theory. We are using Kohlrad theory of elastic rods. Has been around since the early 1900s by the Kohlrad brothers that lived in Paris. And what they did is they modeled elastic rods. And fun fact, continuum robots are kind of elastic rods. They are long in one dimension, and 2 dimensions are really small. So essentially, it's a rod. You can really simplify a continuum robot as a rod. Starts at 0, goes to L. That's the length. We are interested in the red dotted line. And what we can do in closed-rod theory is we can have our world coordinate system, and then we can have a vector pointing to each point along the structure, right? That gives us the curve. And then we also have a frame, a coordinate frame, which gives us the material orientation and the tangent of the curve. And what the closed-rod theory then says is that when you change the state of the rod, it can be completely specified by keeping track of the orientation of the directors relative to the orientation prior to deformation. And what that really means is that we can represent the state of this robot by really looking at this coordinate frame and its location along its length. So what we can do to simplify that is that we look at the bending and torsion of these of the robot at each point along its length. S is like parameterizing the arc length, and at the shear strains as well as the dilatation. And that in total is a vector valued function, so we have only 6 parameters to describe the full state of the robot at one instant of time. And this is all in reference to a reference configuration, usually the straight configuration. We describe the deformation. Now, with the state representation, we can formulate the model by describing the robot kinematics, by describing the equilibrium laws, by using the constitutive relations. I'm not going to go into detail here. And then we can formulate a set of differential equations. So it's important in your 3rd year to pay attention in differential equations if you want to do continuum robotics. Anyway, you can solve this numerically, obviously. And we can do this pretty well. We can do this in real time with a couple of kilohertz even, so it's very powerful. You might wonder, so that's only the theory behind the general case. You have to kind of make this work for your robot and have the boundary conditions which are dependent on your particular robot type. In terms of accuracy, we can do pretty well. So here you see, this is the accuracy for a concentric tube robot, the tubular structure. And you can see here that's a histogram that shows you for 80 measured configurations what the tip error is. So the tip error is down here from 0 to 16 millimeters. And you can see the occurrence of the error. And you can see most of the errors lie below 2 millimeters. And there are some errors in weird cases when there is high external loads where the model is not as good in predicting where the robot actually is. For tendon-actuated continuum robots, it's kind of similar. It's the same histogram style, but I want to draw your attention. So it's 180 different configurations that we have been measuring in this case, so the occurrences are a little bit higher. But you can see also the error is below 2 millimeters usually, which is pretty good for continuum robotics. But obviously much worse than for a serial robot arm. Serial robot arms usually get down to an accuracy of 0.2 millimeters, 0.3 millimeters. So that's an order of magnitude higher. But as a take-home message, what the accuracy we can achieve, it's about 1.5 to 3% in respect of the length of the robot, which is pretty good. All right, so you have seen, okay, closed-rod theory with elastic rod. That sounds like a pretty big complicated thing. It is, but it's also pretty cool, pretty powerful. What you could also do, that's something we have been looking at recently, because everybody's looking at machine learning, right? We kind of want to go with the hype. Anyway, so we measure 64,000 robot tip positions. So we put a sensor at the tip of the robot, and then we just let it move around and measure 64,000 of these positions of the tip. And we record what did we do to the tubes. How much did we translate them? How much did we rotate them? And then we feed this into a neural network. Just one layer was like, I think it was 100 neurons. And then we look at the error. And as you can see, this learning approach is performing pretty well. It's also getting down to about 2 millimeters. So we can also use deep learning in order to solve the kinematics problem. It's just the beginning, so it can be really useful, I think, to discover what kind of unmodeled effects do we really have, and can we even get this closer? For now, we are kind of on par with the physical model. All right, so we can model this robot. So we could help this little elephant to get a model of its trunk, right? So the next question is, how can we plan motions for continuum robots? Now that we know the model, we can obviously think about how can we coordinate what we do on the actuation side in order to have it behave the way we like it. So motion planning is concerned with getting the robot from an initial state to a final state and finding out how to do this. Rather, you could either have it on the shortest path, like a straight line between those, and have the robot travel along it, or you could have some other constraints on your motions, for example. And an interesting thing about continuum robotics is it's actually dependent on the sequence of how you do things. Here is a concentric tube robot that moves from the same initial configuration to the same final configuration, but on the top, we are moving all the joints, so the translation and rotating at the same time, synchronous, to start and stop at the same time. And on the bottom, we are first doing the translation and then doing the rotation part. And you can see the course of the robot motion is very different. And obviously, it makes a huge impact depending on where you're operating your robot, on in which sequence you are moving things around. So that's a huge decision process that goes into motion planning as well. And it becomes even more interesting when you think about all sorts of motion constraints that you might have. An obvious constraint is that you would like to avoid obstacles, right? Your robot shouldn't impair any obstacles or shouldn't interact with them. Or you would want to achieve null space motion. Null space motion was this thing where I keep the orientation of my end effector and then move my arm around, right? So I reorient my robot by keeping the position of the tip fixed. Or I might enforce even more shape constraints. I might enforce that the whole shape conforms to a predefined shape at some of the locations. Or ultimately, I want to have a follow the leader motion where I want to have the robot shape conform to its previous shape while advancing it along a path. And these are very challenging motion planning problems where we have some solutions, but where we also could actually make use of some bright minds like you are to kind of come up with more efficient solutions and more straightforward solutions. Now lastly, now we can model it, we can plan motions for it. So now how can we control this robot? Now continuum robot control is also pretty challenging. Once again, you can apply control methods that you know from control theory. And what we mostly do, and it's more application driven, is that we apply teleoperation. So we have the master of the robot having an interface to kind of orchestrate what the robot should do. We want the robot to actually mimic what the operator is doing. What we do is we use the forward kinematic model, the model that we have just been talking about, and obtain a Jacobian, which is very important in robotics, in order to relate actuator velocities to velocities in Cartesian space. And then the human perception, like you see is the robot actually doing what I want it to do, helps you to kind of reduce the error. That's how it looks like. You see the concentric tube robot and the operator that is using this haptic input device. So the tip of the pen, like in stylus, is then mapped onto the tip of the robot. And the robot pretty much performs the same motion. You can use motion scaling. So you can see this being very helpful, for example, in surgical applications. This is just one of my medical collaborators. We are working on have been working on a project with the vocal folds. This is what you can see. So he's using a regular endoscope back here, and this is the robot, and this is the larynx of a pig. So the vocal folds of a pig, and he is performing the teleoperation motion and just seeing how he gets along. And he really likes the interface. Now, teleoperation is one thing. That's pretty easy. So you do not really need sensors because the user is kind of the perception, the sensor, so to say. So adding perception is actually one of the big challenges. Because of size of the robots are really small, so integration becomes challenging, and also having sensors that are small enough to be integrated is challenging. Also discrete versus continuous measurement. Do you measure the shape only at some point or along the whole body? And also static versus dynamic, and in terms of in terms of time. One possibility is, for what we do in the lab most of the time, is tactile measurement, actually. We use a coordinate measurement arm to really touch the tip, but not really touching it, to not deform it, to kind of get an idea of where it is. Or we could use laser scanners, for example. If we have a static environment, we could just laser scan the whole thing, process the point cloud and so on, and get the shape, then relate the shape to our kinematic model and optimize it. Or we can use camera-based, stereo camera, multiple view, right, to observe what the robot is doing. But that's also pretty challenging because the robot is so small that only very few of your pixels really belong to your robot. So it's actually not that easy to recover the whole shape. We can use something that's called electromagnetic tracking. So we can use these little tracking coils here from NDI. It's a Canadian company that I really like. So these are electromagnetic coils that can be put in an electromagnetic field, and they can be located very precisely. They can be integrated in the robot, and so you can get a discrete measurement of some point along the robot or multiple points. Force torque measurement is really challenging because force torque sensors, this is about one of the smallest, are way too big, right? So we cannot really integrate them into our robot. One exciting technology is fiber break grading technology. That is, you grade an optical fiber and measure the change in the reflection of light, and then you can relate this shift in the spectrum to the strain on the fiber. You can integrate those fibers into the robot, but it's also, well, pretty expensive technology on the one hand. And there's also this trade-off. If you integrate those sensors into your robot, you might lose the working channel, right? If you think about this concentric tube robot, you have this channel to get to the tip, to your patient, but then you have to occupy it with all these sensors. Then you kind of lose the importance to get to where you want to go. Anyway, let's think we get this challenge kind of accomplished, and then we can do automatic control, right? So we can close the loop that we have closed earlier by human perception now with our sensor. For example, here we use the stereo camera to have this robot move to these individual points that are on a chicken breast. So the robot is automatically servoed to reach those points just by visual feedback. So you can see there's this little spherical object on the tip of the robot that what we use as a marker for the stereo camera to observe. And then the robot touches these individual points very precisely, actually below a millimeter in error. So that is pretty exciting work that we have been doing last year with our collaborators. Now, one thing that you might have recognized so far, so these robots are pretty compliant. So how can we deal with this inherent compliance? Because sometimes it might be beneficial, but sometimes it might be not, right? It's advantageous as long as you don't want to harm anybody, right? If you think about, okay, there's a human, close proximity, you want this robot to not harm this human. So you can always say that's an advantage. But it can also be a pretty high disadvantage if you really want to go a place and then you have like some impact, some external force acting on your robot and you're way off where you want it to be. So we have to find a way to adjust the stiffness of the robot when we really want it to be stiff in order to operate, in order to be accurate. And now again, you know by now I'm really excited by animals. So I'm looking at the animal kingdom usually, or we all in the lab are looking at this animal kingdom. And we have gotten inspiration from those objects, like from cones or snake skin or pangolins. So this the skin structure is very unique, so you have these scales that are overlapping partly and induce a higher stiffness, but at the same time you can pretty much maintain the movability. And we kind of used this inspiration to develop a scale sheath. So it's cut out of paper, laser cut. We cut out these scales and then we kind of knit this sheath, pull a latex membrane around it, and then we draw a vacuum. And that causes the atmospheric pressure to put these scales on top of each other, and then the, I'm missing the word. It's too bad when you're German and then you don't remember the word and there's no German in the audience. Anyway, so there's friction. That's the word I was looking. So friction increases. And so that causes this whole structure to stiffen. And that's actually pretty exciting. So that's how you see how we build it. It's this paper material. It's neobond. It's a synthetic paper. It's very tear resistant. And we put it inside this latex membrane. And here's, you can see what happens. So on the left side is the tendon-driven continuum robot. And on the other side, it's the same robot with this tendon sheath around it. It moves into the same spot, so there's no real interference. And then you can see one of my students, she is actually adding a weight of about 1 Newton to the tip. And you observe the deflection. So the regular robot is deflecting quite a bit, right? And then with the sheath in its stiffened state, they move too much. So that's a pretty cool technique. It's less, so the robot is less prone to external forces, and we can really stiffen it up whenever we like to, and whenever we feel now we need high accuracy. We want this robot to stay where it is in order to do something. The stiffness increases up to a factor by 10 to 24, depending on the configuration. There's more research needed, but that's an exciting first result that we got. All right, wrapping things up. So some of you in the audience might now think, should I work on continuum robotics? I hope some of you are thinking that. And what I think, yes, you should. Continuum robots are pretty cool, right? I hope I brought this across. No, but honestly, like, they are pretty cool because they are very challenging in terms of the problems that you're facing. They're challenging because they are nonlinear systems. They're nonlinear because the number of kinematic degrees of freedom approach infinity. And that makes it very exciting because it's really hard to deal with these systems. And they are under-actuated system at the same time because it's impossible to actuate all these degrees of freedom independently and simultaneously. So you have to find a good balance and a good trade-off. And lastly, they are ill-observable because it's impossible to obtain sensory information on all degrees of freedom. So you really have to have a really good idea in order to treat a continuum robot because it has these characteristics. This is the research areas I'm focusing on. You have been seeing them across my talk. In the Continuum Robotics Lab, we are focusing on design, modeling, planning and control, as well as human-robot interaction, all under the umbrella of the applications that I've talked to you earlier about. Now you might think about what are areas worth working on. Some of the areas that I think are particularly challenging, maybe for some of you, is, for example, design and control of soft continuum robots, so getting even softer than the ones that you've been seen here. Designing very long and thin continuum robots, that's very exciting. There are really no good solutions so far. The longest we can build is like about 30 centimeters, but really like build a meter long. That would be exciting because the compliance and the self-weight and like that's all coming into play, and you have to be really creative about what sorts of material you want to use, how you want to actuate this thing, how you want to stabilize it, and how you want to maintain its shape. Cooperating continuum robots is also a field where there's no research at all, so that's a very exciting topic to work on. Or also human-robot interaction. Like we have seen perception to some extent, and yes, you can teleoperate it, but how can you actually make the user perceive the shape of such a robot, where it is when it's sneaking into some area where you lose sight? Right? How do you feedback, maybe even contact on the robot to the human? That's really exciting to kind of think about how can you survey this morphological information to a human user. Explore machine learning for modeling. We've only been talking about forward modeling today. So that means you know how you actuate it and want to know where it ends up. But the question is, inverse modeling is even harder. So you want to tell the robot, well, move here, and I want to know, well, how do I have to actuate it in order to move here? So that's really hard, and there's no closed form solution to that. And I think machine learning could play an important role in order to solve this problem more efficiently. And then shape sensing and control, I've talked about with you. Sensors are a real issue, and then using this information in control, because it's a very high state space. How can you deal with this efficiently is also very exciting. It's kind of my vision behind this, right? In the end, I would like to see this user in this immersive environment being able to operate this robot, these continuum robots, in multiple applications which really benefit our society, if it is, for example, in inspection or in medical applications. I wouldn't be standing here today if I wouldn't be working with all these amazing students. So these is my lab from Germany, how it is currently. Some of them are coming with me to Toronto, and I hope to see some of your faces on this slide at some point. So I'm coming to Toronto April 2019, and if you want to work on continuum robotics, you should definitely contact me. I am in desperate need of having students help me set up this lab in the summer. So if you're excited about continuum robots, come talk to me. Well, that wraps up the conference. I thank you very much for organizing it, and I'm looking forward to your questions.
Thank you so much. Now, if you have any...
Yeah, if you have any questions, go ahead. Yes, please.
I was just wondering, you talked a lot about taking inspiration from like nature and stuff, and one of the things I was curious about when you were talking about using sensors and trying to sense the locations. Like for instance, I know an octopus has its neurons are kind of segmented through its body, so it kind of thinks in different sections of its body at the same time. So I was just wondering, is it kind of, is there some reason that people tend to try and localize all of the control to one part, or would there be some use to like diversify it throughout the part?
Yeah, very good question. I repeat the question for the video. So the question was, can we also take inspiration, for example, from nature, from the octopus that uses sensory information at different locations and also computes it at different locations, if I got it correctly? And can we actually make use of this knowledge from biology in order to optimize control? Definitely yes, but there has been no real good approaches yet in continuum robotics. But it's a good idea to actually distribute your sensors along your shape and probably also the processing. It's just always this trade-off because you're that small in size on how you're going to achieve this. But I think ultimately that's the best solution to do it, to kind of put it along and I kind of have the computation unit with it. That would be ideal. Yeah, and there has been also research looking into what's the best trade-off between the number of sensors and where to place them in order to achieve the most information about your state space. Any other question? Yes?
So for motion planning, is reinforcement learning something that's like often used now, or has that been explored?
So the question was if reinforcement learning has been used for motion planning. Yes, to some extent. There are some research groups that have been looking into it just a little bit, but there has been no major publications on it. So it could be an interesting summer research project, if you ask me. Any other question?
Yes. At the top.
Just curious, but is there like some research into using like actual electrical stimulation of muscles? Because with muscles you can just line the whole thing and then control it with it.
Yeah, it's not research I have been doing, but a collaborator of mine, he is collaborating with a biomedical engineer, and they are printing heart cells to kind of make a robot structure such that it's made out of muscle parts. It's very spooky, to be honest, but at the same time, it's kind of very cool if you could do it. But yeah, I think that's very early research. It's not something that I've been looking at, but I think ultimately that could be a really, really interesting route to explore. Absolutely. Yes.
So when you talk about the degree of freedoms of the robots, and you say that some robots are like hyper-redundant, they have like infinite degrees of freedom. So I was, one of the questions that intrigued me is that how do you actually, like obviously depending on the shape of the robot and depending on the task at hand, the shape of the robot determines whether it's suitable for a different task or a wide range of tasks. So my question is, how do you optimize the morphology of the soft robot itself, and what parameters do you take into account when you try to develop the optimal shape of the robot?
Yeah, that's a very good question. So it's about the design optimization. How do you actually decide on the morphology of the robot depending on your tasks? That's a whole different research area that I haven't been touching on today that we are working on in my lab. I have a graduate student, Josephine. She's going to graduate sometime this summer. She's working on design optimization. And she is using, for example, genetic algorithms to optimize for the parameters of the robot. So you take the task requirements, you take the design space, and you try to optimize all those parameters for some certain interest of you. For example, you want to cover this workspace, you want to be very stiff at this point, and so on. So that is very, very exciting research, but also I think we are still just scratching the surface. So we could really go much further with it. But it's at the same time, so the state space is just really big. The number of parameters to optimize is really, really big. But it's the only way to do it, using optimization algorithms in order to tackle this problem, and also to find efficient ways to formulate what is it you're aiming for, and also to restrict your search space meaningful. Yeah, that's a very exciting area. Design optimization, computational design is something we are working on as well. Thanks for bringing that up.
I have a follow-up question. So when you think about optimization problems, say that you want to optimize a robot for a certain task, like surgery, then you kind of know what you try to optimize for. You know what your fitness function is. However, if you want to optimize, like if you want to develop robots in completely new environments like space, then you have very few information on what you need to optimize for. So how would you approach a problem that where the robot is located in a completely new environment?
In a completely new environment, that's super challenging, right? You would have to come up with some requirements, obviously, like what would be the size of the robot? Like you have to restrict your search space somehow in order to be able to tackle this problem. What you're talking about is more like if you would send, for example, the robot to space, because it's lightweight, right? It might be a good option to use a soft continuum robot. So you would send it up to space. You don't really know where it's ending up. So you kind of have to restrict what it needs to do, but at the same time, you're looking for some universal robot, right, that is able to, for example, put itself in some locations, maybe observe the environment, maybe even lift some objects. So without putting any constraints on your design, you're really screwed, right? So because, no, seriously, like for continuum robots, it's harder. Like you can build a serial robot arm by just, deciding on the link lengths, and this robot is universal. You can use it for all sorts of tasks, changing the end effector. But here we are talking about a much smaller scale, and so you are very application driven. So you cannot really tell there's a universal continuum robot that can solve all the problems. There might be very many individual continuum robots that are suitable for a particular application, for a particular patient even, and even for a particular space application. So I think with this type of robot, it's really hard to find a universal design that suits all the requirements. Thanks. Any other question? You're tired. Oh, there's one question.
Is the amount of actuators needed to control the robot also a big issue?
Yeah, I mean, ultimately, I would like, if you ask me as a student, I would tell you, yes, I want an infinite amount of actuators that you control each individual degree of freedom. But obviously, you can't integrate all the tendons, or you can't integrate all these millions of tubes. So yes, there's always a trade-off between the number of actuators that you use in order to control your shape and what you want to achieve. That's always a trade-off in order to get really small continuum robots as well. All right, well, I will be around for the reception, so if you have any questions you don't want to ask now, you can definitely ask them later. I thank you very much for your attention. Thank you.